I'm a postdoc in the Hamiltonian group, and she couldn't be here, so I'm speaking on her behalf. Our group does two main things on blue waters. They're both related in that they both include non-Born-Oppenheimer effects. I work on one of the projects, and I'm really going to focus on that and kind of only spend maybe half a slide talking about the other one, because you might imagine I'm very much not an expert on the other project. So we are a quantum chemist in the Hamiltonian group, and the starting point of a lot of quantum chemistry, as so earlier said, is just the electronic Schrodinger equation here, so H psi equals E psi. This electronic Schrodinger equation assumes and invokes what's called the Born-Oppenheimer approximation. And what this does, or what it says is, since the protons are so much heavier than the electrons, that the electrons move much faster than the protons, and they basically, the electrons respond and adjust instantaneously to any nuclear motion. And because of this, we can treat the nuclei as just classical point charges, and we can define a potential energy surface that the nuclei move on. We're interested in systems where nuclear quantum effects are important, where you can't treat the nuclei as classical point charges, and we're specifically interested where the Born-Oppenheimer approximation breaks down and that we have nuclei moving as fast as the electrons in chemical systems. So nuclear quantum effects are a very general phenomenon. I mean, you see them in a lot of places. So 0-point energy for like reaction barriers and reaction heights, hydrogen tunneling for reaction rates, and just hydrogen bonding in water. So I think like Peter Roski 20 years ago showed that for ice, nuclear quantum effects could affect the melting point by like 20 K or so. And so to get a proper description of liquid water, you really need to include nuclear quantum effects. What we're more interested in our group are specifically non-Born-Oppenheimer effects, and we're really interested in a specific type of that called proton-coupled electron transport, or PCET or PCET. And what that is we have an electron transferring from a donor to an acceptor, and at the same time we have a proton transferring from a donor to an acceptor as well. And these do not have to be going to the same place, so they can actually transfer at different parts of the molecules. And in these type of reactions, the proton can actually transfer on a faster time scale than the electron transfers. And so the Born-Oppenheimer approximation just fundamentally doesn't work in these type of systems. This is kind of the first project that I don't work on that we do on blue waters in our group. We've developed ways to calculate rate constants for PCET reactions and methodologies for generating the data to calculate these rates. And we've applied them to the enzymatic type reactions. And so that's one broad thing we do. The other thing we're interested in, and so the way you do this is you actually still assume the Born-Oppenheimer approximation, and you couple various electronic states together through non-adiabatic coupling matrix elements. And so we're interested in calculating or figuring out non-Born-Oppenheimer effects without invoking the Born-Oppenheimer approximation ever. And so the way we've developed this in our group is through something called the nuclear electronic orbital method, or NEO method. And it avoids the Born-Oppenheimer separation between electrons and just select quantum nuclei. So we actually have to treat at least two nuclei classically still, and that's some technical reasons. And then from there, once we decided what nuclei we're going to treat quantum mechanically, we just solve a multi-component or mixed nuclear electronic time-independent Schrodinger equation. So this was developed 10, 13 years ago. The Hamiltonian for it is very, very similar to the normal electronic Schrodinger equation. So this top term here, we have three types of particles. We have electrons, quantum nuclei, and classical nuclei. This top term terms right here are just the normal electronic Schrodinger equation if we weren't to have any quantum nuclei. This next right here is for the quantum nuclei. So we have kinetic energy for the quantum nuclei in our Hamiltonian, and nuclear repulsion for classical and quantum nuclei. And then we have a nuclear electronic attraction for the quantum nuclear particle. So from there, we have our Hamiltonian defined, H psi equals E psi. As our ANSAT for our wave function, we write it as two Slater determinants, just a product of two Slater determinants, an electronic and a proton Slater determinant. This is basically just the same as doing Hartree-Fock for normal electronic structure theory. From there, we can apply variational conditions and minimize the energy with respect to the electronic and nuclear MOs. And from there, we get Roton-Hall-like equations, just like you do in normal electronic structure theory. You actually get two equations. You get one for the proton, you get one for the electron, and these two equations are coupled and have to be solved self-consistently together. This is really easy to do, and it's pretty easy to derive. And so it's really unfortunate that since you're treating an electron-proton correlation in a mean field type way, and the electron-proton correlation is attractive rather than repulsive for just normal electronic structure theory, you just get awful results. The hydrogen vibrational frequencies are like off by 1,500 wave numbers, and the nuclear densities are way, way over localized, and it impacts all other properties. You can try doing like MP2 on top of this, but the 0th order guess from the NEO-Hartree-Fock wavefunction is so poor that the perturbation is too large to recover that. And same thing with like doing CI, the CI expansion. You can't do truncated CI. You could do full CI, of course, but it's way too computationally demanding in order to do that for real systems. So this is unfortunate, and is kind of where we were even 10 years ago. And since we know it fails because of the since we don't include explicit electron-proton correlation, the idea is let's put that in there. And so the answer for the new wave function for explicitly correlated Hartree-Fock or NEO-XCHF is we have our earlier product of Slater determinants for the electronic and proton parts, and now we're going to couple them through these Gaussian-type geminals. From here, once again, we can apply a just variational method and minimize with respect to the orbital coefficients, and we get Hartree-Fock-like equations. This gives accurate densities and actually works. The bad news is this is very, very computationally expensive, I don't think we ever applied it to something larger than like helium-hydrogen plus, so like 4 quantum particles. And even that required a lot of computational expense and a lot of computational effort. So we were kind of stuck with this for a while and didn't really know where to go. And the most recent breakthrough in the past 2 years by a former grad student, Andrew Surgising, was NEO-XCHF correlates all the electrons to the quantum proton. And instead of doing that, we're only going to correlate a subset of it. And so it's going to be reduced explicitly correlated Hartree-Fock. And this gives just a huge increase in computational tractability. And it actually ends up giving more accurate results. And that's kind of a technical thing, so we won't go into that. But we get better results only coupling select electronic orbitals to the quantum proton. Some examples of systems about why we can do this. So positronic systems where we couple a positron to an electron. And so those are really coupled closely together and really kind of exist as a quasi-particle in a way. And then we have like PCET, which is what we're interested in. So this is the phenoxyl-phenol self-exchange system. So we have a hydrogen transferring here. The hydrogen, even though it's delocalized, is still pretty localized in space overall. And so it's not going to interact with electronic orbitals that aren't in this region of space. And so the coupling is pretty short-ranged. And so that's kind of the idea of RXCHF and why it works. And so we've been putting that in for the past couple years and kind of generalizing it. But the problem with RXCHF is even though it's much cheaper than XCHF, it's still very, very computationally demanding. So we have to solve 2, 3, 4, and 5 particle integrals compared to normal just electronic structure theory or Hartree-Fock where we have 2 particle integrals, where our integrals look like this. So these are atomic orbitals, or atomic basis functions. We have our geminal elements, and we just have the 1 over R12 operator. The scaling of NEO-XCHF is n to the 10th. For RXCHF, when we have 2 coupled spin orbitals, we have n to the 8th scaling. So equivalent scaling of CCSDT. And it's just a huge number of integrals for realistic systems. I think we have to have something like a few trillion integrals to solve like FHF minus. And we end up having to store, I think it's like 60 or 70 terabytes worth of integrals in memory. And so this is why we really, really have needed blue waters and needed these large computing systems. Our bottleneck is this calculation of these 4 and 5 particle integrals. And we really need a large system in order to store all of them. So in the future, we might like to implement direct methods. But currently, our integral package is so poor that it takes like 2 or 3 hours to calculate the integrals one time. And so we really need to store them in memory. And we're actually working on that with the Todd Martinez group in the hopes to make a better integral package. But Blue Waters really allows us to run on 1,000 nodes, and we can really take advantage of this because of how we split our integral calculations up. Our integrals are called embarrassingly parallelizable. That's partly because we really don't know what we're doing currently, and so we have our integrals implemented in such a way that it's really easy to parallelize. And so we'll have to go back and think through that a little more, but we've really been using Blue Waters as proof of concept and that this method works before we go in and kind of make it faster. And so with Blue Waters, we were actually able to show that, and that's what we've kind of done the last 6 months. So we ran an RXCHF calculation on hydrogen cyanide, where we have 14 electrons, 1 quantum proton. We have 2 coupled electronic spin orbitals. So this is closed shell, so we really just have 1 coupled spatial orbital. And if we look at the density profile here, so this light dotted blue is the NEO-Hartree-Fock. This black is a grid-based FGH 48 grid Hamiltonian, which is considered to be an exact answer, a reference answer. And then this RXCHF, NE, and AE just is how we deal with exchange between coupled and non-coupled orbitals. So it's not really important. But we see that we get, we're closer by about 1,400 wave numbers. And our density looks way, way, way better. So this is for HCN. We've also looked at FHF minus, which I don't have a slide for that. And we also see the same level of accuracy. And so we're real happy because it looks like we finally have a tractable method that actually will give correct nuclear densities and correct stretching frequencies. So now that we have a working method, we've started looking at ways to speed this up because this is still very computationally expensive. I think it took us like 40,000 node hours on blue waters to just do this 3-atom system. And if you look at this MO right here, so this is the coupled MO from that you get out. That's very localized in space. And so there's no contributions to AOs on the nitrogen atom. And so what we've done is implemented RXCHF restricted basis, which this was just accepted last week, where we're only going to include in our coupled MO AOs that are centered on the hydrogen or quantum proton or on atoms that are bonded there. So we can actually exclude all the AOs from the nitrogen. And that results in a really large speedup. It results in a speedup for the systems we're looking at here of like 40 to 50 times. And it also means we can go to larger and larger systems if we only need to include the bonded atoms, because basically this could be a benzene ring over here, and we really see the same scaling because of this coupled electron orbital. The size of that basis really dominates the scaling of our calculation. So when we apply this RXCHF, this is various ways of doing it. But no matter how we really do it, we basically reproduce the full results. And so this combined, I guess RXCHF combined with the restricted basis, we're very, very hopeful in the future that we'll start being able to actually address real chemical problems and stop having to kind of just do proof of concept method development. And for the first thing we've actually done with that, because we've really only looked, I guess HCN and FHF minus are adiabatic systems, and so it doesn't necessarily make sense to have a non-adiabatic method that can only do adiabatic systems. We've implemented open shell RXCHF and looked at HCN plus, which is highly non-adiabatic. And so this is a adiabatic grid calculation, so it's not necessarily the best comparison, but we actually see a shift in that bond distance relative to the grid calculation that we're claiming is due to non-adiabatic effects, and that we're in the process of doing this, but we've been working with David Sepperly's group at Illinois who does QMC, and they have non-adiabatic quantum Monte Carlo, and they're seeing the same kind of shift in that we see. And so this is the first non-adiabatic system we've done, and we're already starting to see things that we can't do with standard Born-Oppenheimer approximation type methods. And once again, just to hammer home the point, where we look at the frequencies here, and we just see NEO-Hartree-Fock is very, very over-localized. So summary of this, the NEO method incorporates nuclear quantum effects and non-Born-Oppenheimer effects between electrons and select protons. We really need to include explicit correlation in order to get an accurate nuclear density, and that if you do a mean field approach for a multi-component system, it is just not going to work. Even with these advances we've made, we still have a huge bottleneck in the computation and storage of multi-particle integrals. And that without blue waters, this is stuff we just fundamentally couldn't run on our own machines that we have in-house. We're starting to actually do real applications, so hopefully next year when we're here, we'll actually have some exciting science rather than just kind of technical developments. And we're still ongoing to develop new techniques within the NEO method. So for this self-exchange system, it's probably really going to need to be multi-configurational. And so we're currently developing 2 configurational NEO in order to do that. And likewise, the other big focus we have is improving our integral package. because with a lot of this, we didn't know if it was going to work, and so we didn't want to spend a whole lot of time making integrals fast for 5-particle integrals that we weren't ever going to use again for a method that we were going to use once. And so now that it looks like it's working, we're going to start doing these 5-particle geminal integrals and doing them right. So acknowledgments. So a lot of people have worked on this in like the past 12 years. The people with RXCHF recently, Chet Swalina, Mike Pack, and a former grad student, Andrew Serjusing, funding from the Air Force Office of Scientific Research, the NSF, and then computer resources. And I'd be happy to take any questions. So thank you. Yeah, sure.
So you mentioned terabytes of integrals, sort of thing. When you run on blue waters, do you scale your node count based on basically your memory requirement?
Yeah. Well, the calculations are expensive enough that we really need to scale up a little higher if we're going to run within the day time limit. But like we cannot run on a single node. I think like 64 nodes is our minimum calculation for certain types of these.